Last time we stopped in the middle of the proof of some theorem. So let me recall. I started broadcasting. So first of all, we defined certain evaluation morphism. Like this. And then we defined certain coefficients. So the complement nu to mu was a vertical strip theta, and then b nu mu was defined as t to n of nu minus n of mu, product over all pairs I and j, 1 minus q to mu I minus mu j, t to the power j minus I plus theta I minus theta j over 1 minus q to the power mu I minus mu j, t to the power j minus I, and here theta, well, I don't know how to say, well, I don't know. Theta I is 1 if ith row, well, how to say, yeah, if ith row contains a box of theta and 0 otherwise. Okay, it's the vertical strip. It has at most one box in each row, and then we proved that the specialization of the elementary symmetric function u lambda times mu specialization of the Macdonald polynomial is equal to the sum of b nu mu specializations u nu of p lambda, the sum over all nu containing mu as above. Okay, and then we were proving theorem 20 of two parts. First, the symmetry part, the specialization at lambda of p mu tilde was equal to specialization at mu of p lambda tilde. So here the length of mu and the length of lambda is at most n, and also well, maybe I can put here p lambda tilde is the renormalized polynomial p lambda over this evaluation u naught of p lambda, which is not 0. Okay, so this was the first part, symmetry, and the second was PRE formula. So p tilde sigma ER is the sum over all nu of b nu sigma p tilde nu. Okay, the sum again over the same set. Okay. Yes. Renormalized Macdonald polynomial. So this is just an element of our field F. So as a polynomial in X, it's just renormalized. Okay, so we're almost there. Well, this formula I will need in a moment. So we proved some big chunk of this theorem. So we proceeded by induction in mu. Well, in A, so to say. First, in the total size and in the lexicographical order. Okay, and then given mu, and some positive integer r such that mu r plus 1 was bigger than mu r, we defined sigma such that sigma I was equal to mu I minus 1 for I at most r. And also sigma I was equal to, well, sigma j was equal to mu j for j bigger than r. So it's a partition by definition, and then model a certain non-vanishing claim about certain well, linear dependence on non-vanishing of determinant. We proved that last time proved that ER P sigma tilde is equal to the sum over all nu as above B nu sigma P nu tilde. That is B for sigma. Okay. This is what we managed to do last time. And essentially here we stopped. And now there was no lambda so far, right? It was only part B for this sigma. And now we move to A and take partition lambda of length at most n. Take u lambda of this equality. Okay, and we get u lambda of ER, u lambda of p tilde sigma is the sum over nu b nu sigma u lambda of p nu tilde. Okay, and by our induction assumption, we know that u lambda over p tilde sigma equals u sigma of p tilde lambda, because sigma is smaller than mu in lexicographical order, or even it is smaller in total size. Okay. And we also know by the same induction assumption the symmetry u lambda of p nu tilde equals u nu of p lambda tilde. Okay, for nu not equal to mu. Hence, this equality becomes u lambda of ER times u sigma of p tilde lambda equals b mu sigma u lambda of p tilde mu plus the sum over all nu that is smaller than mu in lexicographical order, b nu sigma u nu of p lambda tilde. Okay. Now from this formula I encircled above, we get u lambda of ER times u sigma of p lambda tilde is b mu sigma u mu of p lambda tilde plus the sum over nu less than mu b mu sigma of p lambda tilde. And finally, b mu sigma is not 0, hence comparing the two latter equations, we get u lambda of p tilde mu equals u mu of p tilde lambda. Okay, that is A. Okay, now this was all proved modular certain. Yes. So we used the non-vanishing statement. Namely that the determinant of evaluations u pi over p nu over all nu and pi less than or equal to mu was not 0. At all only p tilde. So we can replace P nu tilde by P tilde, sorry, by P nu. Well, this will just multiply our determinant by the product of certain non-vanishing factors. Then replace P nu by monomial function m nu. Since the transition matrix is strictly upper triangular, so has determinant 1. Okay, so have to prove that the determinant of u pi of m nu over pi m nu less than or equal to nu does not vanish. Now, this is a certain polynomial in Q and T, right? And as a polynomial in T, it has the leading term well, maybe not it, but rather any matrix coefficient u pi of m nu has the leading term u pi of x to the power nu, that is q to the scalar product nu pi times t to the scalar product nu rho. The scalar product is just most simple-minded scalar product. So nu pi is just the sum of nu I by I. And rho is, you know what. Okay. So we can consider just the leading term of this determinant. That will be the determinant of leading terms of this. And it suffices to prove that this does not vanish. And now this is certain elementary exercise that that I will eventually include into exercises. But the problem is that I'm afraid today I will not. Again, I will be too slow, and I will not have time to introduce everything for the next meaningful set of exercises about Magdalenic polynomials. So then, instead, I will give some exercises about usual partitions having nothing to do with Magdalenic polynomials. And in particular, I will defer this exercise till after the break. Or you may just solve it state and solve it yourself. Okay. So here we are. And the theorem is proved, and it has the following corollary. So first of all, well, we had this PRE formula, but for renormalized Magdalenic polynomials. Now PRE formula for usual PRE, for usual Magdalenic polynomials, P mu times ER is equal to the sum over lambda psi prime lambda mu P lambda. So again, the sum over all partitions lambda such that the length is at most n, and the complement is a vertical R strip, as always. And now psi prime lambda mu is, well, in fact, last time when I advocated PRE formula and talked about bispectrality, I already wrote a formula for this, but it was, in a sense, the very final version. But at the moment, we only immediately see the following intermediate version. So this is just a direct reformulation of the previous theorem, part B. And now the next claim is that the evaluation at 0, which is by definition P lambda of 1, t, so on, t to the n minus 1, actually equals t to the power n of lambda, lambda specialization of delta plus over the 0 specialization of delta plus, where this delta plus, there's certain rational function in Q and T, is the product over all pairs, as always, of the following Pohammer symbols: xi over xj, Pohammer symbol over t, xi over xj, Pohammer symbol. And from this, we will deduce the formula I announced last time, so that psi prime lambda mu is the product of 1 minus q to mu I minus mu j, t to j minus I minus 1, 1 minus q to the power lambda I minus lambda j, t to the power j minus I plus 1, over 1 minus q to the power mu I minus mu j, t to the power j minus I minus 1, sorry, j minus I, 1 minus q to the lambda I minus lambda j, t to the power j minus I. Okay, and the product is over all pairs such that lambda I equals mu j and lambda j equals mu j plus 1. Okay. So as I said, A is an immediate reformulation of the theorem, and let's prove B. So it is clear for lambda equals 0, and both sides are just 1. Nothing to prove. And now note that if lambda equals mu plus 1 to the r, so we just add 1s to the first r parts of mu and do nothing with the others. It's like what we did to this sigma to obtain mu. So in this case, we get psi prime lambda mu is 1. Just comparing the coefficients of x to the power lambda. So this is just definition. Okay, and then it follows that we already know for lambda. Well, even without this, we know that the evaluation of p lambda at 0 is b lambda mu evaluation of p mu at 0. Well, for lambda equals mu plus 1 to the r. Okay, so we have this, and we will use it later on. Let's mark it with exclamation mark. Because of this, it suffices to check that the evaluation of delta plus at lambda over evaluation of delta plus at mu equals t to the power n of mu minus n of lambda b lambda mu. For mu equals lambda 1 minus 1, lambda 2 minus 1, so on, just lambda with the first column removed. also mark this. Now both sides of this equality we are going to prove are products of binomials, or maybe products and ratios like 1 minus q to a, t to b, so products or ratios of such things. And we will use the additive notation, just as for characters of say Lie groups or tori. Okay, so for such a product, like M, the product over A, B, 1 minus q to the A, t to the B, for some power n a b. So NAB is an arbitrary integer. We set L of M. This additivization is the sum over all A and B, N A B times Q to A, T to B. And so this is a formal power series in Q and T. Okay, and then it's clear that L is injective. And hence it suffices to check that L of the left-hand side of our equality equals L of the right-hand side of this formula. Okay. So let's consider the simplest product. So it's Pohammer symbol, Q to the A, T to the B, Pohammer symbol. Okay. Let's compute what is this additivization. So what do we get? So this thing is 1 minus q a t b times 1 minus q a plus 1 t b times so on. And well, all n's are just ones. So what do we get? Yes. Just by the geometric progression. Nice. And it follows for our delta, that is just the product of Pochhammer symbols, or maybe ratio of such. Here? No, I think it's. Well, just from the geometric progression. So we have QA TB plus QA plus 1 TB plus QA plus 2 TB. Yeah. So it's QA times TB times 1 plus Q squared plus Q cubed and so on, which is 1 minus Q inverse, right? This is definitely true. So if we compute additivization of u lambda of delta plus over u mu of delta plus, then we get the sum over all pairs u lambda of xi over xj minus u mu over xi over xj times 1 minus t over 1 minus q. Yeah, just because here we have something divided over t, this something. So this gives you the numerator 1 minus t, and the denominator we just computed. Okay. Also, we know that evaluation u lambda over xi over xj minus evaluation at mu of xi over xj equals q to lambda I minus lambda j minus q to mu I minus mu j times t j minus I, just by the very definition. Still up there. Okay, so this equal to q to the power mu I times q minus 1 times t to j minus I for I smaller than the length of lambda and less than j, and 0 otherwise. Now, so let us set R equals L of lambda for abbreviation. Okay. So now let me erase definitions. I mean, I use here that mu is obtained from lambda just by removing the first column. That's why lambda I minus lambda j is either mu I minus mu j or okay. So we conclude that L of u lambda of delta plus over u mu of delta plus is the sum to the length of lambda, the sum from the length of lambda to n, q to the power mi, t to j minus I, times t minus 1. Okay, and by definition of b lambda mu, which I just erased, but hopefully you still have it. L of t n of mu minus n of lambda b lambda mu is equal to the sum over all pairs ij, q to the power mu I minus mu j, t to the power j minus I, t to the power theta I minus theta j minus 1. So here, as usual, theta I equals 1 for I less than or equal to length of lambda, and 0 otherwise. Okay. And now we compare this and that. And they're just the same. So we are done. L of so we wanted to prove this formula, and that's it. Okay, but we still have to check this explicit formula for C, for psi, right? So for the Curie formula. Okay. So we have psi prime, by definition, is b lambda mu, evaluation at 0 of p mu over evaluation at 0 of p lambda. And by part B, which we proved, we get that this logarithm additivization of psi prime lambda mu equals the sum over all pairs I and j, q to the mu I minus mu j, t to j minus I times t to theta I minus theta j minus 1 minus the sum over all pairs q to mu I minus mu j, t to j minus I, q to theta I minus theta j minus 1 times 1 minus t over 1 minus q. And this is the sum over all pairs q to mu I minus mu j, t to j minus I, t to theta I minus theta j minus 1, minus q to theta I minus theta j minus 1 times 1 minus t over 1 minus q. Okay. Now we want to compute this sum. Okay. Now the pairs I less than j such that theta I equals theta j give the 0 contribution. And the pairs such that theta I equals 1 and theta j equals 0 also zero contribution. But if theta I is 0 and theta j is 1, then this expression equals 1 over t minus 1 minus 1 over q minus 1 times 1 minus t over 1 minus q. And this is t inverse plus q inverse t minus 1 minus q inverse. And that's just what we wanted. So C is proved. Okay, so finally we did prove the yes. We just wanted to compare the logarithms, the relativizations of the right-hand side and of psi prime, and we computed the left-hand side. And well, these are the 4 terms of the right-hand side. Well, so you know that lambdas are either mu's or mu plus 1. Yeah, they are obtained by adding a few boxes to the right, well, you should just consider those 4 or whatever, those cases. Yeah. Okay, so now we will make some formal manipulations with this with this formula, and we write it in terms of arms and legs, just equivalent reformulations of Peary formula. So we define for a box S with coordinates ij in the Young diagram of lambda. We set the arm length A of S is lambda I minus j, arm colength A prime lambda of S is equal to j minus 1. The leg length L lambda of S is lambda j transposed minus I, and the leg colength L prime lambda of S is I minus 1. So we have some S, box X, S, then A is the number of boxes to the right of S. A prime is the number of boxes to the left. L, number of boxes below of S, and L prime above. So, well, this is for A, this is for A prime, this is for L, this is for L prime. But I mean strictly to the right, strictly to the left, strictly above, and strictly below. So it's related, for example, to the hook length and to the content and to other statistics. For example, you know, in Scientology or whatever, there is a notion of Hirsch index. No, you haven't heard yet. And do you know what is this Hirsch index? Well, you have papers, and each paper has a certain number of citations. And you obtain a Young diagram. The most cited paper, the next one, and so on, with the number of citations. And then you just compute the length of the diagonal. This is the Hirsch index. So, as I said, the hook length H of S is just 1 plus A of S plus L of S. And the content C of S is A prime of S minus. So our next lemma 22 says that the specialization of a Macdonald polynomial at 0 0 P lambda, and this is equal to T to the power n of lambda, product over all boxes in our Young diagram. 1 minus q to the power a prime of s, t to the power n minus l prime of s, arm and leg co-lengths, 1 minus q to the power a of s, t to the power l of s plus 1. And this is all about diagrams of length at most n. So we have to check that the sum over all boxes of q to the power a prime of s, t to n minus l prime of s, minus q to a of s, minus t l of s plus 1 equals 1 minus t over 1 minus q, the sum over all pairs, q to the power lambda I minus lambda j minus 1 times t to j minus I. Well, again, after applying our logarithm relativization. But we, yes? Yes?
Как у нас произведение в знаменателе, которое было, превратилось в сумму?
You mean this, yeah? That was my, sorry, typo. I didn't erase it. Okay, so we know that the sum over all boxes of q arm co-length, t to n minus leg co-length. By the way, it makes sense, yeah? The leg goes down and the arm goes horizontally. But in French notation, this is very obnoxious. Would be very obnoxious. So we have this sum, and this is the sum over all I of 1 plus q plus so on plus q to lambda I minus 1 times t to n minus I plus 1. So I mean, for each I have the same t part and add all the possible q contributions. So 1 minus q times this sum is the sum over all I at all, 1 minus q to lambda I times t to n plus 1 minus I. And this equality, let us mark it, and I will use it later on. So on the other hand, the right-hand side of our lemma can be also regrouped. So when we consider the sum of q to the arm length times t to the leg length plus 1, then the contribution of the ith row of lambda is the sum from I to the length of lambda q to the power lambda I minus lambda j plus so on plus q to the power lambda I minus lambda j plus first plus 1 times t to j minus I plus 1. And this is the sum from I to the length of lambda, q to the lambda I minus lambda j minus q to lambda I minus lambda j plus 1 times t to j minus I plus 1 over 1 minus q. Okay. And now we add up over, well, sum up over all the rows. And we get 1 minus q. Well, if we multiply by 1 minus q, then the sum over all boxes of q to the a, t to the l plus 1 is the sum over all parts t minus q to lambda I times t n plus 1 minus I minus 1 minus t times the sum over all pairs q to lambda I minus lambda j t to j minus I. Okay, now if we apply this formula I marked above, we get well, we get just just this equality. Okay. Well, I'm almost out of time, but maybe let me just formulate one more lemma. So let u be a new formal variable. We wanted to prove the equality of two logarithms, this and that. So this just follows from that. Okay, and then new evaluation, epsilon u t from our symmetric function ring to the ground field is the homomorphism that takes the generators power functions PR to 1 minus u to the r over 1 minus t to the r. So, for example, if this new variable is t to the n, yes? Yeah. Power sum. So then this is 1 minus t to nr over 1 minus t to the r. So this is just PR of 1, t, and so on, t to the n minus 1. And hence, for any f symmetric function, its specialization t to the n t of f is equal to the evaluation like this. Okay, so now let me formulate one last lemma, and we will be free for vacations. Yes. Sorry. Yes, you're right. Thank you. So this evaluation of p lambda equals the product over all boxes t to the power L prime of s minus q to the power a prime of s times u over 1 minus q to the power a of s t to the power L of s plus 1. Okay. And the proof is very short. So by the previous lemma, this holds true for u equals t to the power n for any n where this lemma is applicable, so it is bigger than length of lambda. lambda is fixed, and for big enough n, this is just the content of the previous lemma, but both sides are polynomial in U, and since they coincide for infinitely many values of U, they are equal. Yeah, that is a strange, maybe dirty trick, but it is rather useful in various areas of mathematics. Say in representations of semi-simple Lie algebras, like if you are interested in Harish-Chandra's center of the universal enveloping algebra, then you can prove the Harish-Chandra theorem, identifying the center in a similar way. So you evaluate the center at Varma modules, then at irreducible modules, and you know about finite dimensional irreducible modules. They are pretty rare, but there are infinitely many of them, and it's enough to compare just some formulas, just enough to compare for them. And then they will follow for arbitrary highest weights that are indexed by a certain vector space, but it's enough to compare just on the lattice or just a cone inside, monoid inside this vector space. Okay, thank you. And you still have to distribute tangerines.